Cloud RAN deployments rely heavily on the performance and robustness of the supporting compute infrastructure, but are able to shine when multiple important hardware and software elements are all working in harmony. Well, to find out about what makes a Cloud RAN purr, I'm talking today with Adnan Boustany, Director of the Wireless Access Business Group at Intel, Gil Hellmann, VP of Telecom Solutions Engineering and Architecture at Wind River, and Jeffrey Lee, Associate Technical Director of the Telco business at Quanta Cloud Technology, or QCT. So welcome everybody, glad to have you all here today. Adnan, let's start with you. Are COTS-based RAN platforms ready for deployments at scale, both with standard MIMO and massive MIMO deployments? And how is the ecosystem coming along for production-grade virtual RAN software?
Sure. Good day, everybody. Thank you for the question. So if I was to kind of maybe give you some context here, maybe try to help answer the various topics that are covered in that question. So Intel has been investing in the flexRAN program for nearly a decade now, and these investments actually cover both the software, the silicon, and the platform. You will see in the diagram that actually the flexRAN as a program is kind of an enabling overall architecture for delivering vRAN, cloud-native RAN deployments. Now, if you look at those three ingredients again, the software, the silicon, the platform, if I start off with the software, so we have kind of started this journey where we're really focusing on enabling the ecosystem partners. So we have actually delivered software solutions within the flexRAN framework that cover the various standards from 4G to 5G. We did actually focus on 4G first because a lot of the work during the last decade was really about deploying 4G. Remember back from 2011, 2020. And if you look at some of the announcements that was done for some of the early Open RAN deployments back in 2018, 2019, a lot of the work we did with the 4G FlexRAN was meant to enable those with our ecosystem partners. But really, over the last few years, we've really focused a lot more on 5G because we could see, starting probably about 2 years ago, there was a lot of momentum by the comm service providers to start deploying 5G. So the work we did there was really focused on both millimeter wave and sub-6 gigahertz. For those of you who know, in the US, there was a lot of work done for millimeter wave deployments. In the rest of the world, there was a lot of work done for sub-6. So what we did in the case of 5G, we did actually focus on enabling all the various use cases that we see today. So that covered both the narrow bandwidths, so typically 20 megahertz. It also covered up to wide bandwidth, example 100 megahertz. And we also made sure that we can cover both standard MIMO, again, typically 4x4 MIMO, all the way to massive MIMO, which is typically 64T, 64R. Now, the second component of what we have done to enable the ecosystem has been the silicon. And if you think about this, it's great to have software, but actually software development goes hand in hand with silicon. So when we look at our FlexRAN architecture, we really focus a lot of effort on understanding how best to utilize the silicon features in the Xeon processors. And there's actually various techniques and features in the Xeon that can be used for the RAN workload. AVX512 is one such example. And AVX basically means Advanced Vector Extensions. And they help you do a lot of the complex type operations that you see in a typical layer 1 or signal processing domain. And we've actually done various white papers, webinars on these topics. I mean, there's a good few examples if you go onto the internet to find this stuff. There was a good example done by Daniel Towner, one of our colleagues here, and how to build an efficient 5G NR base station as well. Now, at the same time, from a silicon perspective, as we can see, the networking demands continue to increase. And we need to make sure that our silicon roadmap actually lines up to those ever increasing network requirements. So the things that are typically measured tends to be cell densities, as in how many cells can you fit within a certain platform. And then for each cell, can you start to increase the capacity of that cell? So we have been making the right silicon investments to make sure that the silicon, from a CPU perspective, can meet up to those kind of ever-increasing demands. We did actually also look at complementary silicon. So when you're building a base station, the CPU for us is at the heart of the DU, or the base station processing unit. But there's also other components that help the base station communicate to things such as the radio units. And for this, we have things like what we call the Ethernet silicon. And Ethernet silicon, it has various ways of deploying this from, say, centralized RAN to distributed RAN. And especially if you're going to go to distributed RAN, there is a requirement to a bit more accurate timing and synchronization from the base station unit to the radio units. So if you look at some of the products we brought to the market, we have brought in products such as Westport Channel, which is essentially a timing-enabled NIC card for those kind of use cases at the distributed RAN deployments. Other examples of silicon investments we have done also include devices such as the ACC 100, which is essentially an FEC acceleration device for those use cases that require it to be run in hardware as opposed to doing this in software. The third pillar of what I mentioned between silicon, software, and platform is another aspect that we really focused on, and that is because to put the whole thing together, you need to put it into a platform. And what we have actually done is we looked at how to put the platform together for the various use cases. And we actually did this investment at the platform level to cover the use cases you typically see in an outdoor deployment. So you could have your base station deployed at the cell site. It could be in a cabinet. It could even be pole mounted. And we have worked with various hardware manufacturers to bring these solutions to market as well. Now that's kind of from the hardware portion of the platform picture. There's also the software story of the platform picture. So the cloud infrastructure is very, very important. In the early days, a lot of the work went into a virtualized implementation. Now there's a lot of momentum towards containerized implementations. And certainly the work we're doing with our partners such as Wind River has helped big time to help our customers make best use of both approaches, be it a virtualized implementation or a containerized implementation. And in fact, putting all these ingredients together, you can actually see how we kind of have packaged this into nice, easy, consumable kind of blueprints. So if, for example, you go to the Intel Select Solutions website at Intel, you will see how we have packaged all these things for what we call the virtualized radio access network. And we've done this for all the software cloud infrastructure partners that we work with today. Then just to add a few more things. So if you kind of were to search on the internet as an example to see kind of how has flexRAN been adopted by the ecosystem, given all the investments we have made, you will see essentially kind of partner announcements that covers all the various ecosystem partners. You will see announcements with the likes of the cloud software infrastructure partners like Wind River. You will see vRAN software vendors like Ericsson and others as an example. And then you will see platform partners such as Quanta and others like Dell, HP, etc. And then the final end customers who really will be deploying these solutions such as Verizon, Dish, Vodafone, and many, many more. And this is kind of a good kind of testament to all the work that we have done within Intel and with our ecosystem partners to enable this. And maybe just as a final comment, to kind of package the whole thing together, the initial momentum for vRAN was to enable a virtualized COTS-based implementation of what was traditionally done in custom platforms. But we're kind of going one step beyond this. So we're looking at other innovations in the ecosystem. So maybe two things worth highlighting here. So we're using the flexRAN platform to also enable the other use cases that come within, such as the O-RAN Alliance when they're defining the RIC. So if you look at the internet, you will see we have done some work with companies such as Juniper, Cohere, on enabling some nice functionality that will be very, very useful for the RIC implementation. We're also working with various comm service providers for doing some interesting topics on the next wave of features. Again, if you Google, say, Intel FlexRAN URLLC, you'll see a white paper that we have done with IEEE that is kind of going to be published with Verizon on how to enable URLLC on the FlexRAN architecture.
Okay, thanks, Adnan. Gil, let's come to you now. How is the enabling software from container as a service vendors adapting to the needs of various centralized RAN and distributed RAN deployments?
Sure. Thanks, Ray, for the question. First, let me start with Adnan mentioned the journey of how much Intel invest in creating the flexRAN reference implementation. Windoverse partnered with Intel pretty much at the beginning, to go through this journey, and over the time we learned a lot. And if we're looking at basically what are the key important things, especially to successfully deploy vRAN, there are a couple of things. One, it's to make sure that it's cost efficient. Cost efficient, it means the overhead of the platform need to be such that it's very low. So if we're looking at, for example, distributed RAN, we're talking about the ability to deploy basically a virtual DU on a single server with a single socket, so it fits the power consumption requirements and the size requirements of those sites that it's going to be deployed. And if we're looking at a massive MIMO, 64 receive, 64 transmit, it means that you need to basically fit everything within a processor that has, for example, 32 cores or even less. Okay, so the overhead of the platform need to be such that allows you to do this. It also need to be providing you the performance that you need. So basically, ultra low latency, virtual RAN, 5G NR. It's one example of a URLLC type of use case. But really, we're talking about a platform that need to provide you the ultra low latency, to provide you the low, small, ultra low footprint. And then the other thing, it's the ability to scale. So if we're looking at going from a DRAN to a CNRAN to a centralized RAN, those cloud clusters need to be able to scale, okay, and scale in a way that it's dynamic. So basically, don't need to stop the service while you're adding more capacity to the site. 5G NR radio access network, it's, as I mentioned, one example of URLLC use case. But really, at the end of the day, there will be other use cases that will be placed at this edge locations that will be connected to the VDU through, for example, a user plane function like a UPF, local breakout. Okay, so the ability to grow this cloud cluster dynamically, it's a very critical element. Okay, and if we're looking at the deployment architecture that we have in the slide that you can see, it's basically what we call a geographically distributed cloud. So from an operator perspective, it's the ability to deploy all those edge location, far edge locations where the DRAN sites and the CRAN sites will run from a single location in an automated way and manage them in an automated way. So those are very critical pieces that the CAS layer need to be able to support. So it's not just simply deploying containers across different sites, but it's the whole day zero and day two operations that are critical pieces.
Okay, thanks, Gil. And Jeffrey, let's come to you now. Are hardware platforms also being optimized specifically for radio access network deployments?
Thanks, Ray. It's a good question. There are many COTS servers in the planet at this moment. However, QCT Iron Edge server was designed and optimized for Open RAN deployment. Our EGX63IS1U is front access, which can meet carrier customer easy installation and maintenance demand. The base station shelter always comes with the space constraint, so our Iron Edge server is ideal for this purpose, as the depth is only 220 mm to accommodate with more server environment at the far edge side. Our edge server provides a wide operating temperature range from -5 to 55 degrees Celsius. With a single circuit in one node design, it provides a better granularity option in various sizes of the base station scenario, from single sector to multiple sector by stacking server as demand. Moreover, our hardware specifications are compliant with many industry standards, such as NAPS Level 3, ORAN, and OTIS standards. Our QCT EGX63 IS is based in a class edge server for RAN deployment with its cost-effective, high-performance, excellent feasibility design. Thank you.
Okay, thanks, Jeffrey. Let's come back to you, Gil. What's being done in terms of software optimization for the RAN?
Yeah, a couple of things. I mentioned the first, starting with the ultra low latency. Okay, the cloud platform, the CAS that comes from a Wind River over the year was highly optimized to deliver the lowest latency that is possible. Okay, which is critical when you deploy those URLLC type of use cases. We also work on optimizing the footprint, as I mentioned, to make sure that the platform overhead is very, very minimal. What minimals, if you may ask? It's 2 physical cores to basically give you a complete cloud cluster, so control plane and computer worker in the Kubernetes. So in the Kubernetes term, it's a master and a worker on a single server, with all the functionality that you require for day 0 and day 2 operation. So like, for example, headless patching, in-service upgrades, all those capabilities. So you can run basically your VDU, everything on a single box. Now, I mentioned that and it was mentioned at the beginning here also, that on the CPU side, things are evolving all the time to basically keep up with the demand for more capacity and more cost optimization, reducing of power consumption. On the same way on the software side. So we work very closely with Intel and with a partner ecosystem on the hardware side. So QCT is one of them, to basically constantly optimize the software side. So consume less and less resources. So as I mentioned, the platform overhead is already very low. And we're basically working with Intel and the ecosystem on the next generation where the platform overhead will be even lower. And in addition to it, enabling in the cloud platform, in the software capabilities in the silicon that will allow you to run a video application and any other type of URLLC type of application, and in a more optimized way and consuming less resources, consuming less cores, for example. Okay, so again, constantly improving the both power and cost equation, as well as basically what can you do with a platform, okay, and increase the demand. So like I said, those are things that we already done and we continue to do to improve it.
Okay, fantastic. Thanks, Gil. Adnan, let's come back to you. Can you tell us about recent baseband software optimization developments that are now available to the RAN ecosystem?
Yeah, sure. So maybe 2 good examples would be, I think the first example I would say is around the massive MIMO technologies. The early work we did for flexRAN, as I mentioned previously, was really focused on what we call standard MIMO. Standard MIMO is typically 4x4. That usually means 4 antennas, 4 receivers, and usually the layers kind of line up to the antennas. So if you have 4 transmit antennas, you typically have 4 transmit layers. So there's a lot more complex processing that has to happen, especially in the receiver chain, to kind of go from one domain to another. So the layer domain to the antenna domain. So we did a lot of work, in fact, to really implement this as efficiently as possible. Again, utilizing the best techniques within the Intel CPUs. And again, AVX512 was one example, but there's other things we have utilized to make this happen. And we did this kind of really starting about maybe 18 months to 2 years ago, to kind of give our ecosystem partners the early view of how they can go about upgrading their existing software that was done for standard MIMO into massive MIMO. And again, we delivered this in terms of massive MIMO as a complete L1 implementation, so that we have all the required building blocks done that our ecosystem partners can build upon. Another example would be, there's a new silicon device coming out next year. It's going to be coming out in 2022. It's called Sapphire Rapids. This will have some new enhancements at a silicon level that we think is going to provide a significant performance jump in terms of cell density, cell capacity on the Intel CPUs. So we've already started to develop the software that takes advantage of those enhancements on Sapphire Rapids. And now we're starting to provide this to our ecosystem partners as well, in anticipation of them adopting those platforms in 2022.
Okay, important advances there. Thanks, Adnan. And Jeffrey, how should all of these developments come together to create a carrier-grade solution? And how have partners such as Intel, Wind River, and Quanta made this a reality?
vRAN platform needs to consider lots of features other than the traditional virtualized workload. In addition to real-time requirement, it also needs to consider other features such as acceleration card, time synchronization, and the network capability for the front haul. It can make it unless the hardware and software collaboration closely. In this project for ISS, we use ICC100 as a FEC acceleration card to offload CPU computing power with more power efficiency by eASIC technology. With Intel E810 NIC card, it can provide a 2 port of 100 gigabit per second, which support high data rate for the front haul. This advantage right fit the high order MIMO systems and the high dense cells deployment at the base station side. Besides, E810 NIC card can support the GPS function to provide time synchronization for the 5G RAN deployment. As mentioned before, Wind River Studio support Baseband RAN cloud native platform. We integrate this software stack in the Intel Ice server along with the several Intel expansion card. QCT validated it to be a high efficient platform, which reaches a high ratio line rate of the network card and also the low packet loss and the low jitter. With this pre-integrated, pre-validated, pre-optimized platform for the vRAN, it can dramatically help carriers shorten their network deployment time for the high stable infrastructure.
Okay, so lots of different developments coming together there. Adnan, maybe we can come to you for a closing comment for today's conversation.
Yeah, thank you. So maybe in a closing comment, I would say if you're trying to build a RAN network that is based on virtualized cloud native type technologies that scales from, say, centralized RAN to distributed RAN, covers the macro segment to rural and small cells, and then supports the various 3GPP technologies, I would say please come and talk to us here at Intel, Wind River, or QCT, and even the wider ecosystem who's adopting these technologies to bring kind of the right solutions to their overall comm service providers.
So Adnan, thanks for concluding there, and thank you all, Adnan, Gil and Jeffrey, for joining us today to talk through these important Cloud RAN developments. Thanks very much for joining us.
Thank you very much.
Thank you very much.
Thank you.
And don't forget to watch the other programs in the Intel Network Builders vSummit series. As well as vRAN, we're taking an in-depth look at the network core, edge and security. Thanks for watching and goodbye.